Moment generating function is that's the function, then we can generate the moment. Yeah, that's what it means. So we find out the moment generating function m equals the expected value of the e to the power e of the power to the at the tx. Okay. So provided the expected expectation exists for t in a neighborhood of 0. So you have to have an expectation t is very close to the 0. That have to be exist. If it doesn't exist, then the moment generated function doesn't exist either. Okay, and then so actually this is not the moment. This is not moment, but we want to find moment, right? So even though it says it's a moment generated function, but this is not a moment. So what we can do? This is the moment, case moment. This will be the case derivative of this moment generated function, and then when t equals 0. That's why the expectation should be 0 near the t. Is it easier or better than the integration? Yeah, let's take a look at it. And first, I wanna explain how this one working. Okay, e power to the tx is a 1 plus tx. This is the Taylor series expansion, so you can find out it's a e power to the tx equals 1 plus tx plus t square x square over 2 factorial plus and so on. It will be going forever. But since this one, the denominator is getting bigger and bigger, so the size of term is getting smaller and smaller as it's goes by, but it will go infinitely. Okay. Now, moment generated function is defined by the expected value of e to the power of tx equals 1 plus t. So what I'm doing is taking expected value here both sides. And the expected one is 1. The expected value of tx is a t times expected value, because this is about expected about the x. Right? Here the expected value will be t squared is just number, so taking out, and 2 factorial divided by 2 factorial is just number, and it will leave the expected value of x squared. And this is a cube, expected value of x cube, and so on. So first moment, by definition, we have to take a derivative one time, right? So expected value, first moment, is the one derivative over t of expected value of e to the power tx. But if you take a look at it here, if you take a derivative on t, 1 is not a function of t, so it will be 0. And then here, this is the function of t, but t expected x is a constant from point of view of t, right? I am taking derivative again regarding t, so expected of x is not function of t, so this is just like considered as a constant. That's why the derivative is just expected of x. But however, this part, what we can tell is that this is you have a 2t, so actually derivative part will be the 2t times expected of x squared over 2 factorial. But we have to put the t equals 0, right? So if you put t equals 0, this one becomes 0. That's why it's a 0 here. How about third one? Third one will be 3t squared times something something, right? So expected of x cubed divided by 3 factorial, but again we have to put t equals 0, then this one will become 0. So everything will be 0 because later we have a t power to the 4, t power to the 5. You will have a t, but when you plug t 0 into the plug t, then everything will be 0. This one doesn't have, after derivative doesn't have a t, so only this term survive. Second momentum, if you take a derivative 2 times against the t and then put the t equals 0, then you are taking derivative one more time. So 1 take a derivative twice is a 0. Here take a derivative once, it becomes ex, and then you have to take a derivative one more time, then it will become 0. However, this is a first derivative, so now 2t x squared divided by 2 factorial, but if you take a derivative one more time, it will becomes 2e x squared divided by 2 factorial, right? So these two will be cancelled out, and then only expected of x2 remains. And then after that, if you take a derivative of this one, it will be you will have a 3t squared, and then if you take a derivative one more time, this will be the 6t, right? And then put the t0 here, then everything will be 0 afterward, all 0. So when you take a derivative, first derivative, you will have only the first term, nothing will remain because we put the t equals 0. And if you do take a second derivative, only the second part remains, and everything else will be the 0. So that's why actually this satisfied our definition of the first moment derivative, the first moment and the second moment. So if we utilize this moment generation function, maybe we can get a moment way easier than the integrals. So now we go back to the exponential with the moment generation function. So moment generation function is this way. So we just calculate this one, right? And this is what? This is my value, and this is probability. PDF. Right? Moment general function is like this. Now we have to make sure, because it's the same base E and E, lambda going out, and then it's base E and E, so we can just simply add up. So like A B times AC is the A B plus C, right? So using this one, we can just add a Tx plus minus lambda x, and you can see the power becomes a t minus lambda x. And then since this is the integral, so you can just actually do the integral, and then you got this one. Now if you wanna calculate, this is a moment generation function, you wanna find out the first moment. What you can do is simply take a derivative of this one, moment generation function, and then put t equals 0. So take a derivative here. You can find out this is the case because t is in the denominator, and then put t equals 0. Then this will be lambda over lambda square, which is a 1 over lambda, and that's the result you can get. This is the same result we got here, right? So first momentum is the mu is 1 over lambda. So we don't have to do these integral things. We can just simply take a derivatives, right? And easier. So we can do the expected value of the x squared. Just simply take because this is a second derivative. you can just take this one, take a derivative one more time, then you will get this one, and then put the t equals 0, then you can simply find out is a 2 over x lambda square will be your second momentum. But second momentum is related to your variance. So variance looks like this. So you can calculate this is a second momentum minus square of first momentum, and you can find the 1 over x squared. This is your variance. If you don't recall why the variance is this way, then we can if you want to know why the variance, the definition of variance is the 1 over n and sigma xi minus mean square, right? This is the variance definition. And again, the summation and divide by n is the same as the making an expectation. So this is just expectation of xi. So now it's not 1, 2, 3. I can just simply put x minus m, which is a mean square. Right? So I'm gonna expand. This is the expectation of the square. So if you just expand this one, this will be x squared minus 2mx plus m squared. Right? So this is just, you can just separate out x squared minus expected of 2mx plus the expected of m squared. But since if you know the characteristic of the expectation operator, if this is multiplied a certain constant number, you can just take it out. So 2m can go out. Is a 2m expected value of x, and m itself is just a constant number, so it will be just m squared. Yeah. And then think about what is the mean. Mean is just expected value of x, right? So you can just replace this into the over m. Then what will happen is the expected value of x squared minus 2 expected value of x times expected value of x times expected value of x squared. So this is also expected value of x squared. So if you just look at expected value of x squared minus 2x squared plus 1x squared, so you can just leave a minus expected value of x squared. So this is your variance. That's how this formula, right, is the same as your variance.